Hi there everyone. Today's video is going to be another real deep dive into a technical aspect of FPV technology. This video is actually a request from It's Blunty. He wanted me to look into the gyros that we use on our flight controllers in some detail and try and come up with a comparison between the different types of gyros and maybe a recommendation as to which gyro is the best one for you to use and what filter settings you should set depending on the gyro that you have. So that's what we're going to cover today. Let's get into it. We're going to start with a detailed explanation of how MEMS gyros work. We're then going to look at datasheet specifications for all the common gyros. Then we're going to look at some apples to apples bench tests that I've done to see how the gyros compare against each other on the bench under controlled conditions. We're going to discuss some of the different modes that these gyros have and why Betaflight uses the modes that it does today. And finally, we're going to finish with some recommendations on which gyro you should look to get if you've got a choice, and what the best filter setup is for each gyro. So how do MEMS gyros work? Well, MEMS stands for Micro Electromechanical System, and these are electromechanical parts fabricated using the same masking and etching processes that are used to make microchips on silicon wafers. A MEMS gyroscope uses the Coriolis effect to sense rotation. They have two masses that vibrate towards each other and then away from each other, so that those two masses are always moving at exactly the same speed but in opposite directions. When the system is rotating, these moving masses experience a force due to the Coriolis effect. And this force is proportional to the rate of rotation of the gyro. The force causes the masses to vibrate in the y direction on this diagram at the same frequency that they vibrate in the x direction. And by measuring this vibration in the y direction, you can determine the rate of rotation. So what is the Coriolis effect? Well, let's imagine that we have a mass and it's moving from point A to point X. Now, if this red disk here is not rotating, the path from point A to point X is a straight line. And so we're not going to see any force acting perpendicular to the path. However, if the red disk is rotating, that path from point A to point X actually ends up tracing a curve as that red disk rotates. Now, whenever we have a mass moving along a curved path, we're going to have a centripetal force that keeps it moving in that curve. And that centripetal force is going to act in this direction perpendicular to the path. This fictitious force we can detect in the rotating coordinate system, and it's called a Coriolis force. And you can imagine if you have a mass that's very rapidly oscillating back and forth between point A and point X, you could measure this perpendicular force to determine how fast the red disk is rotating, how fast the gyro is rotating. So here's the structure that's typically used to measure this effect in a MEMS gyroscope. There are two masses, here they are in green, and these two masses are vibrating in opposite directions. So they're both vibrating along the drive axis here, but they're vibrating either towards each other or away from each other. They're always moving at exactly the same speed, but in opposite directions. And this means that any Coriolis force that is acting on these masses is going to act in the perpendicular direction to the direction of drive. So I've labeled that the sense axis. And because these masses are vibrating back and forth in the drive axis, then the Coriolis acceleration is going to cause them to vibrate in the sense axis as well. And by looking at the amplitude of the vibration in the sense axis versus the amplitude of the vibration in the drive axis, we can determine the rate of rotation around the z-axis, which is going into or out of the page. Because the masses are moving in opposite directions all the time, any Coriolis force is going to be equal but opposite for each mass. and this allows any noise that's affecting both masses the same to be rejected. This is called common mode rejection, and it improves the signal to noise ratio. So if we look at a normal amplifier, a single-ended amplifier, and we have this signal in blue, and we have this noise in orange, then when we add the orange noise to the blue signal, we get this sort of noisy signal here, which is amplified, and that's what we get out. If, however, we have two signals that we know are equal and opposite, so we have one signal here that's positive, and exactly the same signal here, but with the opposite sign, so a negative version of that signal, and we have noise that's added to both signals equally, then we can subtract one signal from the other signal. And when we do that subtraction, the noise that's been added to both signals equally will cancel out. And the two signals that are equal and opposite will double in size, because if you take x and then you minus x, you're going to end up with 2x. So this common mode rejection allows us to double the size of the signal whilst also removing all of the noise that affects both the signals equally. So how is the structure of a MEMS gyro made in practice? Well, the MEMS gyro is made on a silicon wafer. So this is a wafer here, it's a circular disc of silicon, and all the structure for the gyro elements is etched into this wafer using photolithography, masking, and then etching processes. The CMOS circuitry, with all the electronics that's needed to drive and read the gyro elements, is made on a second wafer. These wafers are then diced, which means that all of these individual chips you can see here on this massive grid are cut out. The MEMS gyro wafer is then bonded to the CMOS wafer using these metal interconnects here. And all of the connections between the CMOS electronics and the electrical elements and sensing elements in the MEMS gyro are bonded through using these metal interconnects. The whole finished silicon is then soldered to the lead frame using these bumps here, and this lead frame is a piece of copper which is what's going to be soldered down onto the final PCB. And then that whole lead frame and silicon assembly is encapsulated in the black plastic that you see when you look at the gyro from the outside. So now that we know how the gyro is made, let's look at the specs of all of the common gyros that we use on our flight controllers and compare and contrast them. We've got the MPU6000, the tried and tested, the MPU6500, which was popular for some flight controllers a while ago, and then we have the newer gyros from InvenSense, the 2602 and 2689, and then this BMI270, which is used on just a few flight controllers like the iFlight Beast F7 V2. They all have a lot of similar specs. They have the same full-scale range of 2000 degrees a second. They have the same resolution of their ADCs, 16 bits. And they all have a low-pass filter. But here's where we get some differences. The MPU6000 and 6500 use a 256 Hz low-pass filter. The 2602s use a very similar 250 Hz low-pass filter. But the BMI270 uses this much higher 750 Hz low-pass filter. And we'll see the effect of that difference in a little bit. The output data rate of all of the MPU and ICM gyros is very, very similar. Although it should be pointed out that some of them have a 32 kHz mode as well as an 8 kHz mode. And we're going to be talking about the difference between 8K and 32K later on as well. When we look at the noise spectral density, which is a measure of the sensitivity of the gyro to noise, again we can see that all of these gyros have pretty similar noise spectral density. Maybe the MPU6500 comes off a little worse here with the highest noise, but all of them are around 0.005 degrees per second per square root frequency. We can also see that the mechanical frequency of the gyro, which is the frequency at which those two masses are vibrating back and forth is very similar for all of the MPU and ICM gyros at about 27 kilohertz. Really, just looking at the specs, there's not much to choose between these different products. I want to take a moment now to talk about production status of these parts, because there's a general concern within the FPV community that the MPU6000 might be going out of production or might not be being made anymore. All of these gyros, including the MPU6000, at the time of this recording are still in mass production, which means they are still making large quantities of the MPU6000 and the 6500. However, both of these parts are not recommended for new designs, and that suggests that InvenSense are looking to move people over to the ICM26 series instead. And in fact, when you look at the MPU6000 page, it recommends you to use the 2602 instead. That said, they are still making these parts, so new MPU6000s are going to be available. Obviously, at the moment, there's a bit of a chip shortage, so the lead times are pretty long, but we can be confident that we will have flight controllers with MPU6000s on, certainly for the foreseeable future. Let's look now at a comparison of the BMI, ICM and MPU gyros on the bench. Now, I only have the 2602, the MPU6000 and the BMI270 to test, but hopefully this will give you an indication of how these different gyros perform. All of these gyros were tested with the same frame and motors, and I produced these graphs by running the quads on the bench with the motors spinning at 2500 RPM for 1 minute while logging. So this is the test setup. And I want to be super clear at this point that I'm doing this so you don't have to. I have the props upside down, so it's pushing down into the bench. And also I'm running using the motor testing tab, so the PID loop isn't active, so there's no way that the quad can flip out. Nonetheless, I would never advise anyone to run the motors on the bench with the props on. But you do need the props to generate a representative amount of vibration for these gyro tests. So needs must in this case. I then processed the logs in PID Toolbox to produce these power spectral density charts. What we can see is that the MPU6000 and the BMI270 really delivered, I think, equal best performance at low frequencies. And I would say that the low frequency performance is by far the most important, because we don't filter low frequencies in Betaflight at all. Because these low frequencies are flight frequencies and we want to understand what's going on at these frequencies, so we don't apply any filtering. That means that any noise that appears in these low frequency plots is going to go straight through to the PID loop with no filtering and going to cause us hot motors and problems like that. I felt that the ICM2602 was less impressive at low frequencies. You can see it's a little bit higher across the whole range, but it's only very marginal. But it did seem to do better at higher frequencies, which honestly I think is less important, because at those higher frequencies, 300, 400, 500, 600 hertz, we have loads of low pass filtering active that's going to prevent any of that noise getting through to the PID loop. So I think it's really this sub 100 hertz region where we should be really focusing on noise performance. Now, if we look at the BMI 270, you might be surprised to see that the noise from the BMI 270 is very, very much higher than either the MPU 6000 or the ICM 2602 at high frequencies, let's say 600 to 900 hertz. It's much, much higher. And we need to understand why that is when the noise performance of the gyro is so good at low frequencies. Well, it all comes down to the hardware low-pass filters in these gyros. All the gyros that we're looking at have a digital low-pass filter as part of their design. And we call it the hardware low-pass filter because it is implemented inside the gyro hardware. But we should be aware that it is still a software filter, similar to those that Betaflight use, but it's just running inside the microprocessor in the gyro rather than inside the microprocessor in Betaflight. Both the MPU and ICM gyros have this filter cutoff at about 250 Hz. But the Bosch gyro also has a digital low-pass filter, but its cutoff is at a much higher frequency, about 750 Hz. And this explains the difference that we saw in these two graphs. You can see that at 250 Hz, we now start to get the low-pass filter in the ICM and MPU gyros kicking in and attenuating the noise. But for the Bosch gyro, we really don't have that filter kicking in until above 750 Hz. So we end up with much more noise, particularly in this region above about 350 Hz. If we look at a black box log of a flight now, we can really see the difference. Now, while this wasn't the same flight, these were similar flights on the same frame and with the same motors. So hopefully we can draw a comparison. But you can really see how the low-pass filter on the MPU gyro starts to attenuate the noise very hard above about 400 Hz, and we don't see almost any noise above that frequency. Whereas the BMI270 has quite similar noise performance at low frequencies, but then this huge spike of noise at around 600-700 Hz before again we start to see its low-pass filter coming in and attenuating the noise at higher frequencies. So these digital low-pass filters inside the gyro really do matter for the flight performance of our quads. During my research for this video, I discovered a poorly documented feature of the BMI270 gyro. It turns out that the BMI270 has an oversampling mode within its digital low-pass filter that can be used to reduce the filter cutoff from the normal cutoff of 750 Hz down to 300 Hz. This would make it much more similar in performance to the MPU6000 and ICM gyros. But it's not documented in the BMI270 datasheet at all. In fact, it's only documented in the datasheet of a similar part, the BMG250. I'll put links down in the video description if you're interested. I'm working with the Betaflight developers on this, and hopefully the improvement can be included in Betaflight following appropriate testing. But I've already managed to build a version of Betaflight with OSR4 mode enabled. And this is what I found. You can see here the red line. This is the BMI270 gyro in the normal mode. You can see that big hump of noise before the low-pass filter kicks in. Our favorite gyro, the MPU6000 in the dark red, obviously a much lower noise level. And then the BMI270 gyro with OSR4 mode enabled, if anything, looks even better than the MPU6000. The low frequency performance of all three gyros looks very similar, so OSR4 mode hasn't affected the low frequency noise. But on all three axes we can see a big improvement between the BMI270 normal mode and the BMI270 OSR4 mode in terms of the noise above 350 Hz. Some of you may be aware that in the past, Betaflight allowed higher gyro sampling rates than 8K. Back in the day, we used to run 32K gyro update rates and 16 or even 32K PID loop. And some firmwares, like Flight 1, may still use 32K update rates. Well, both the ICM and BMI Gyro can run faster than the maximum rate that Betaflight uses. The ICM26 series and the MPU6500 gyros both have a 32 kHz mode, and the BMI270 gyro has a 6.4 kHz mode, but Betaflight only uses a maximum of 3.2K sample rate on that gyro. The reason that we don't use these modes with higher sample rates is simple. They have a lot of noise, especially at low frequencies. Let's start by looking at the BMI270 gyro. Now, there is both a 3.2K mode and a 6.4K mode, and when we compare the power spectral density of those two different modes, we can see that there is a huge amount more noise with the 6.4K mode than the 3.2K mode. In fact, the difference is about 6 dB. If we come across and compare that to the 2602 at 32K versus 8K, we can see the difference is even bigger. There's 24 decibels of difference in the noise power between the 32K mode and the 8K mode. And this is noise that we cannot filter out with low-pass filters in Betaflight, because you can see that I'm only looking here at frequencies up to 100 Hz. These are flight frequencies, and we don't want to filter them out because we want to see what the quad is doing at frequencies below 100 Hz. And so that noise that you see here is going straight from the gyro into the PID loop and into the D term, and it's going to be causing a lot of problems with hot motors and oscillations and potential flyaways. So why are these modes so noisy? And I have to be honest, this next bit is speculation on my part. I believe that in 8K mode, the MPU and ICM gyros use oversampling, 16 times oversampling. And if they do, this would reduce the noise power by about 24 decibels, which would make sense from what we saw in the graph before. However, in 32K mode, it does not appear that either the MPU or the ICM gyros use any oversampling or averaging at all. It looks like they just give you the raw output from the gyro, and that carries with it a lot more noise. I think the same is true for the BMI gyro, because 3.2K mode appears to have 4 times oversampling, and that would make sense because there is hints in the datasheet for this gyro that it has a kind of raw update rate of 12.8K, but you just can't access data at that rate, but it is collecting it. If we look at the 6.4K mode, that appears to have absolutely no oversampling and averaging at all, and it's probably just the raw output from the MEMS, which means that it carries with it a lot more noise, and that explains the 6 dB of increase in noise that we see when we move to the 6.4K mode. I think what's interesting to see here is that when we move from 8K to 32K, that's only a 4 times increase in frequency. So we should expect to still be able to have at least 4 times oversampling. But we don't appear to have that active at all. And again, with the BMI gyro, if it has 4 times oversampling at 3.2K, it should still be able to have 2 times oversampling at 6.4K. But again, it appears that there's no oversampling or averaging in effect at all. So it may be that these modes are not really designed for use as anything other than debug modes or experimental modes. For those of you who might not be familiar with oversampling, oversampling is when you sample a signal at a multiple of the target output data rate, so usually twice or 4 times, 8 times, etc. Typically, you then average the oversamples together to make good samples at the target data rate. So, for example, if you wanted a data rate of 1 kHz, you might sample at 2 kHz and average 2 oversamples together to make each output sample, and then you'd end up with 1,000 output samples per second, but each of those samples would be composed of the average of 2 oversamples. When you oversample an average like this, you do get a big benefit in noise. In fact, the noise power reduces by the number of oversamples that you take. So if you use 4 times oversampling, you reduce the noise power by a factor of 4. If you use 16 times oversampling, you can reduce the white noise power by a factor of 16. So it makes a really big difference. So that brings us to some recommendations. The MPU6000 still appears to be the best performing gyro according to my testing. It had a slightly lower level of noise, particularly at low frequencies, than any of the other gyros. The ICM20602 is not far behind it at all, and I think it's a perfectly fine choice. And I would expect all ICM26 series gyros to perform similarly. So the ICM20689 is probably going to perform exactly the same. I would not use 32K mode with any gyro due to this lack of oversampling. I would stick with 8K mode no matter the firmware. Otherwise, you're losing out on noise performance quite significantly. The BMI 270 gyro performs very well, but it is going to require extra filtering due to its much higher low-pass filter cutoff. I would recommend that you set Gyro Low Pass 2 to 250 Hz biquad if you have the BMI 270 if you have noise issues. And again, I would not use the 6.4K mode due to the lack of oversampling. I would stick with 3.2K. You can find this setting in the filter tab in Betaflight, and these are the values that I would suggest. I hope you enjoyed that real technical deep dive into how MEMS gyroscopes work, how they're made, how we use them, and which gyro is right for you, and how to set up your filters to get the most out of the gyro that you have. I couldn't make these videos without the support of my patrons, and if today's the day that you feel like I've earned your support, then I'll put a link to my Patreon down in the video description. You can join from just a few dollars a month, and you'll get access to a special area of my Discord server, as well as sneak peeks of the projects that I'm working on. And I've got lots and lots of new frames in the works that only my patrons know about. That's all I have for you for today. So until next time, I wish you all very, very happy flying.